Last October, Thinking Machines published what's become the canonical post on a technique called on-policy distillation. And Quen used on-policy distillation to post-train Quen 3. They released the Quen 3 technical report with the exact numbers. In their Table 21, the Reinforcement Learning Pipeline, RL for short, took 17,920 GPU hours and scored 67.6 on AMY, the competition math benchmark. In contrast, on-policy distillation took just 1,800 GPU hours. That's a tenth of the compute, and it scored higher, 74.4. So on-policy distillation is cheaper to run, and it scores higher. Which raises the obvious question, what actually is on-policy distillation? The name itself is the answer. Distillation means a student model learns from a teacher model. And on-policy means it learns on its own answers, not the teacher's. So the student writes its own answers exactly like RL. But instead of one verifiable reward at the end of each attempt, the teacher grades every single token. You get dense feedback at the price of trusting a teacher. In the next 20 minutes, we'll understand it and implement it. In fact, here's on-policy distillation, the complete implementation, 6 lines of PyTorch. You can already see the shape. The student samples at the top, the teacher grades in the middle, and the update lands at the bottom. It may look alien right now, and that's fine. By the end, you'll understand all 6 lines. Now, let's start with the motivation. Why does on-policy distillation exist at all? To see why, we go back to the Quen 3 technical report from the intro. If you haven't met Quen, it's Alibaba's open weights model family and one of the most used open models in the world. Don't take my word for it. This is Hugging Face's download chart, and the top Quen models get downloaded tens of millions of times every month. So when this team documents exactly how they post-trained Quen 3, head-to-head across the classic training recipes, that comparison carries real weight. So let's give the report a proper look this time. Here's the comparison, Table 21 from the intro. The highlighted row is the first recipe, one we skipped earlier. The report calls it off-policy distillation, and it's the same shape as classic supervised fine-tuning, SFT for short. A teacher writes the solutions, and the student trains on them. It's cheap, but it plateaus at 55 on their benchmark, because the student trains on someone else's text and never sees its own mistakes. The second is reinforcement learning. Now the student writes its own attempts and gets graded. That fixes the mistake problem, and the score jumps to 67.6. But look at the price tag, 17,920 GPU hours, and each attempt is hundreds of tokens of work, yet it earns exactly one number of feedback. On-policy distillation, or OPD for short, keeps the part of RL that works, the student learning on its own attempts, and makes the feedback dense. A grade on every token. That combination scores 74.4 for just 1,800 GPU hours. So where does this idea come from? The story starts in 2015, when Geoffrey Hinton and his collaborators asked a question that sounds almost backwards. Instead of training a small model on the right answers, what if it learned from a big model's full output probabilities? Those probabilities carry more than the answer. They carry how the big model thinks, which alternatives it considers, and how confident it is in each one. And that's the paper's own claim, on screen. Soft targets just means these full probability distributions instead of the single hard answer. And they provide much more information per training case than hard targets. Hinton's team called the paper Distilling the Knowledge in a Neural Network, and it became the standard recipe for shrinking models. But notice the limitation. The student still learns from fixed text, so it still never sees its own mistakes. That missing piece is exactly what a DeepMind team fixed in 2023. They observed that a student trained on fixed text drifts off course the moment it writes its own answers, because nobody ever graded its own writing. And it's right there in their abstract, a distribution mismatch between the text seen during training and the text the student generates. So they flipped the loop. Let the student write and have the teacher grade every token of it. That's the DeepMind paper called On-Policy Distillation of Language Models, known as GKD, and it's the paper to cite. The Thinking Machines post from the start is what made the technique take off. And that post from Thinking Machines, the AI lab founded by OpenAI's former CTO Mira Murati, shows the technique doing something genuinely surprising, so let's walk their story. Here's the problem Thinking Machines faced. A company wants an assistant that knows its internal documents. They started from a model that follows instructions well, call it Checkpoint A. But it has one gap. It has never seen the company docs. The natural fix is mid-training, which just means continuing to train the model on those documents until it absorbs them. And it worked, but something else broke. Look at the red box. The model knows the docs now and it forgot how to follow instructions. That failure has a name, catastrophic forgetting, and it's one of the oldest problems in neural networks. When you push new knowledge into a network, old behavior gets overwritten. Here's the twist that makes this story worth telling. The fix was on-policy distillation, with Checkpoint A itself as the teacher, the model's own past self. It still follows instructions perfectly well, so it grades the damaged model's attempts, token by token, and the green arc carries you to the last box recovered. Docs kept, instruction following back. And here's the receipt from their post, with the 3 numbers circled. Read the instruction following column with me. 85% before, in the blue circle. Crushed to 45 by the mid-train, the red circle. And back to 83 once Checkpoint A does the teaching, the green circle, with the docs kept. So a teacher doesn't need to be bigger or smarter everywhere. It just needs to know something the student lost, and the teacher can be your own past self. So on-policy distillation is 1/10 of the cost, labs are shipping it, and it can even repair catastrophic forgetting. So we're left with the question you're probably already asking. How does on-policy distillation actually work? How does a teacher grade every single token? There are 3 classic ways to teach a model, and the map on screen sorts them by 2 questions. Who writes the text and who grades it? To feel how the 3 differ, we need one concrete problem. So, say we're training a small model to do arithmetic. The prompt is 2 plus 3 times 4. The right answer is 14. Multiplication comes first, 3 times 4 is 12, plus 2 is 14. But a student model can go wrong in a very natural way. Left to right. 2 plus 3 is 5, times 4, 20. Keep that wrong attempt in mind because all 3 methods will have to deal with it. The first way lights up on the map, supervised fine-tuning, the one you've already seen. On our problem, the teacher hands over a worked solution. 3 times 4 is 12, then 2 plus 12 is 14. The student copies it, token by token. And there is the problem. The student only ever sees perfect text. When it makes its own mistakes at test time, it has never trained on any. The second way is reinforcement learning. Now the student writes its own attempts, plural, and the environment checks each final answer. The first attempt is our left to right one. It lands on 20. 20 is not 14, so the reward is 0. Another attempt happens to get it right. 14, reward 1, and RL reinforces the path that worked. That check is verifiable, which is genuinely great. But notice what the feedback is, 1 number for a whole attempt. So for the failed attempt, which step was wrong? And the third way is on-policy distillation. It takes the exact same attempt, but now a tutor marks every step. The step that did addition before multiplication, the equals 5, gets slammed and everything downstream barely gets touched. Every token gets its own grade. And naturally you'll ask, where does this per token grade come from? Hold that question, we answer it in a minute. Now put the 3 side by side, and let's read the table row by row. The first row covers who writes the text. It's the teacher in SFT and the student in the other 2. The second row is who grades it. In SFT, nobody grades, you just copy the target. In RL, it's the environment checking the final answer, and that check is verifiable. In distillation, it's a teacher model, so the grade is dense, but it's a model's opinion. The third row is the feedback each one gets. The full target text, 1 scalar per attempt, or a grade on every token. The analogy row says the same in plain words. Copying worked solutions, taking a pass-fail exam, or a tutor correcting each step. And the cost row is the receipt from Quen 3 you saw in the intro. The last row, when each one fails, stays empty for now. We'll fill it in near the end. So what exactly is that per token grade? To turn the tutor into code, we need its math first. The tutor's per token grade has a real name, reverse KL. It measures how far the student's probabilities drift from the teacher's. Here's the background in one breath. A language model takes the prompt and outputs a probability distribution over its whole vocabulary, a score for every possible next token. It samples one, appends it to the prompt, and repeats. That's how the student wrote its attempt, and it means at every position we can ask both models for their full distribution over what comes next. Freeze the attempt right at the fork. The context so far is 2 plus 3. The student's distribution over the next token puts 90% on equals 5. The teacher puts 2% there and 88 on times 4. The little bars trailing off are the rest of the vocabulary. The gap between those two bars is the penalty, measured in log space, the natural scale for probabilities. Log of 0.9 minus log of 0.02, about 3.9. Hold on to that number. Here's the same thing as math. The expectation is over X sampled from the student's own tokens. That is the on policy part. Inside the bracket, you take the student's log prob minus the teacher's log prob. How much more the student believes in this token than the teacher does. Flip the sign, and you have a per token advantage you can plug into any RL update. And here are all 3 training loops in one picture. They all share the same shape, and the labels on the left name the 2 seats, who writes and who grades. Compare the RL column and the distillation column. The only difference is who sits in the grader's seat. That's why this is one line of code away from RL. So you've seen the same object 3 ways. The bars, the formula, and next, the code. And once you understand the formula, the code is just a translation of it, line by line. Remember the 6 lines from the intro? Let's write them and run them on the toy. To follow the code and keep 3 tensor shapes in your head, B is the batch of rollouts, T is the number of tokens per rollout, and V is the vocabulary size. At toy scale, that's 1 rollout, 4 tokens, and a vocab of 8. The first line is the rollout step, where the student samples its own answer. This produces a B by T tensor of tokens, and it's exactly the same first step as in reinforcement learning. Lines 2 and 3 are twins. Run the student and the teacher over the same rollout. Each forward pass gives log probs over the whole vocab, B by T by V. Quick note, a probability sits between 0 and 1, so its log is negative. Closer to 0 means more confident. Gather picks out the log prob of the token that was actually sampled, which brings the shape back to B by T. Line 4 calculates the formula by subtracting the teacher's log probs from the student's, token by token. That subtraction is the reverse KL. Line 5 turns those grades into a loss. Detach the grade so no gradient flows through the teacher's opinion, then weight each token's log prob by its grade, and take the mean. And here's why that works. When the optimizer minimizes this loss, it lowers the probability of every token the teacher penalized, in proportion to the penalty. That's the same trick RL uses to turn advantages into updates. Then comes the finish you already know. Backward to compute the gradients and step to update the weights. Now let's run the code on our toy. Every row of this table is one variable from the code, its shape, its value on our toy, and how to read it. The first row is the rollout itself, the 4 tokens the student wrote. Equals 5, then 5 times 4 equals 20. The second row is the student's log probs, and they're confident everywhere, all near 0. The third row is the teacher's, and they're mild everywhere except one spot, -4 on the equals 5. The teacher hates exactly 1 token. Subtract them and you get the fourth row, the grades, 3.9 on the fork and 0.1 everywhere else. 1 token carries about 97% of the signal. Flip the sign for the last row, the advantage, and the fork gets slammed at -3.9. Let's do a quick check. Where does the teacher slam the student? Is it the wrong answer at the end? No, the penalty lands right at the fork, on that single red token. The green outlines mean the teacher would have written those tokens too. Look at the equals 20. Its penalty is just 0.1, barely touched. And that makes sense. Given equals 5, then 5 times 4, 20 is correct arithmetic. The mistake happened earlier. The teacher punishes the forking token, not the final answer. Now go back to table 21 from the intro and look at the GPU hours column. The gap between 17,920 and 1,800 is exactly what density buys. A 500 token rollout means the student wrote 500 tokens. RL checks the final answer once. One signal for all that work. Distillation gets 500. So we just built on-policy distillation, and it works. Now the more interesting question, when does it break? There are cases where the teacher's signal is invalid, and the method makes the student worse. This January, Meta, MIT, and ETH all landed on the same idea within 3 days of each other. The idea is called self-distillation, and before we read their papers, let's understand what it actually proposes. Here it is in one picture. On the left, on-policy distillation as we've built it. A student, say Quen38B, writes, and a separate, stronger teacher, Quen332B, grades every token. On the right, the new proposal. Keep the same loop, but the teacher is the same 8B model with exactly one advantage. The reference answer is pasted into its prompt. That advantage has a name, privileged information, and it just means the answer sheet. And in code, the whole proposal is one changed line. Same 6 lines you already know, but look at line 3. The call to a separate teacher is crossed out, and in its place, you call the student again, fed the prompt plus the answer. Now the titles read themselves. Meta's is called Self-Distilled Reasoner, and it grades reasoning traces this way. MIT says self-distillation enables continual learning, using it to add new skills without losing old ones. And ETH's is reinforcement learning via self-distillation, plugging the trick into the RL loop. The appeal is obvious. Why pay for a teacher at all? Let the model hold the answer key and grade itself. That would make the teacher free. Self-distillation backfired, and a follow-up analysis from the original GKD authors published brutal numbers. Their write-up from this June already sits at 140,000 views, and its title says the whole verdict. Why on-policy distillation works and naive self-distillation doesn't. Read the pull quote with me. The self-teacher referred to feedback it never received, flagged on about 96% of chemistry prompts, 98 on tool use, and 80 on math. And that's just the first bullet. The write-up lists the damage in 3 straight from the post, and it shows up in the students themselves. Read the second bullet with me. Their self-checking collapsed from about 86 self-check tokens per response to under 10. And the third, out of distribution on problems unlike their training set, they landed 6 to 25 points below plain RL. So why did it backfire? It comes down to competence versus privilege. On our toy, a competent teacher can take 2 plus 3 times 4 and derive 14 by itself. A privileged one just reads 14 off the answer sheet. And peeking at the answer is not the same as knowing how to derive it. It just makes you good at rationalizing backward. Look at the difference side by side. The left column is the real teacher. It holds the ability to derive the answer. Its grades ask whether each step is sound reasoning, and what the student learns is reasoning that transfers. The right column is the self-teacher. It holds just the final answer. Its grades ask whether each token agrees with the key, and what the student learns is rationalizing backward, which is worthless once the key is gone. That's exactly what the measurements show. Self-checking collapses because double-checking looks wrong when you're holding the key. And performance falls apart out of distribution because rationalization doesn't transfer. Now, there are 2 things this does not mean. First, ground truth is fine, as a verifier. That's RL's honest, sparse reward. The failure is promoting an answer-holding copy of yourself to a dense teacher. And second, self isn't the crime either. Your own past self works fine for repairing forgetting, because that checkpoint genuinely has the behavior you lost. So the rule is, the teacher must know something the student can't fake from context. What if the student and teacher use different tokenizers, the piece that chops text into the tokens a model reads? The math needs teacher log probs on the student's exact tokens, so a vocabulary mismatch breaks the recipe. The workaround on screen is Hugging Faces Gold, a general on-policy logic distillation. It aligns the 2 vocabularies and ships open source in TRL, Hugging Faces training library. It's young, so the same tokenizer family is still the happy path, but if you're mixing model families, Gold is where to look. 3 more questions people always ask. What if the teacher sits behind an API that doesn't expose log probs? Then on-policy distillation is off the table. Fall back to SFT on its outputs, or pick an open weights teacher. Can the student surpass the teacher? No, the teacher is the ceiling, and pushing past your best model is what RL is still for. What if the teacher thinks differently than the student? Forcing a mismatched reasoning style can hurt, so pick a teacher whose style the student can actually imitate. You've seen this table before, so let's go straight to the last row and fill in when each one fails. SFT fails because the student never sees its own mistakes. RL fails when one number can't tell you which step to fix. Distillation fails when no real teacher exists, when nothing knows more than the student does. All three loops are lit one last time. That's the whole map. And after all that, here's the whole video in one table. What should you actually use? Each row of this table is one situation. Find yours in the left column, and the right column is your answer. If a strong teacher exists and shares your tokenizer, use on-policy distillation. If you're pushing past your best model with nothing above you to distill from, that's RL. And if you just need to copy a teacher's behavior without its log probs, use SFT. That's on-policy distillation. The student writes, the teacher grades every token, the fork gets fixed. And it all fits in 6 lines of PyTorch.